Hello and welcome to our webinar From Prototype to Product with Scan-to-Print Solutions from Creaform and 3D Systems. My name is Annik Reckers and I'm working at Creaform. Together with Tobias Klein, Technical Support EMEA Geomagic Solutions, we will conduct you through this webinar. If you have questions, you have the possibility to ask them at the end of the webinar by entering your question in the field Question. I now pass the word to Tobias.
Hello, I'm Tobias Klein, and I will show you the webinar From Prototype to Product. We cooperate in this webinar Creaform and 3D Systems, and I will show you briefly what we will see. We will have an introduction about the workflow. We will have a look at the devices and tools such as Creaform 3D scanners, the Geomagic Solutions 3D scan-based design software, and 3D Systems 3D printers. And today's live demonstration is about how to create a manufacturable product from raw scan data using Geomagic Design X. And at the end we will have a Q&A session. Let's have a look at the workflow. On the left side we have the input side. So here we have, for example, 3D scanners. Here the Creaform scanners GoScan 3D and HandyScan 3D and LetraScan 3D. But you can also use computer tomographs or MRI or any point cloud or mesh generating device. And in the middle we have the processing side, and processing is done in a 3D scan-based design software, which is our Geomagic Design X software. This software converts interactively mesh or point cloud data into parametric history-based 3D CAD software, CAD models. And this CAD model is maintainable and can be altered and can be modified to make it fully manufacturable or fully printable. And we can also get 3D mesh again, which is watertight and which can be forwarded to a 3D printer, for example. So in the right side here we have a selection of 3D printers from 3D Systems as well. Those are the productive machines. Let's have a look at the input side first. So here we are talking about Creaform 3D scanning technology. Why scanning? Because some parts are not easy to touch probe. So, for example, on a CMM or with touch-based, with arm-based touch probe, because some parts are slightly deformable, so very unstable, or have curved surfaces, so they don't rest very easy on the place and move around, or in case you need massive data, not only specific points, then the scanning solution from Creaform is very useful, because scanner is self-referencing itself on the scan on the part, and so you always get the data from the part. So there are several obstacles to overcome in scanning technology. As I already said, the part doesn't rest easy on the place, or there are some vibrations or temperature changes or something, or operators experience varies. And Creaform developed a true accuracy technology which guarantees that these obstacles are taken into account and the accuracy is stable. So there are some application areas for those scanners. Here we can see surface reconstruction and Class A surfacing and rapid prototyping 3D printing. This is the application we want to have a look at today. Part to CAD inspection, non-contact inspection, as I had told before. If probing is not possible, then these scanners can do the inspection. Or first article inspection, clay model, digitizing, or packaging design. Here is an example from the company called Benninger Bus, and they are using the HandyScan 3D to capture the shape of this flywheel and model it in DesignX and check the accuracy in Verify. Geomagic DesignX and Geomagic Verify are 3D systems programs, and the HandyScan 3D is from Creaform. And what you see here is also the VX Element software. It's data acquisition software as well from Creaform. Here you can see on the left side the completed scan of this flywheel as it displays in Geomagic DesignX. And on the right side you can see the final volume model which was modeled based on this scan and overlapped with this scan in DesignX. So when I'm talking about Geomagic, what is Geomagic solution software? Formerly there was a software Geomagic and Rapidform, Alibre and Sensible, and additionally we have a cooperation platform which is called T Platform, and all those software teams united under the brand Geomagic Solutions. So Geomagic Solutions is a combination from all these softwares, and depending on the application we provide the correct package. So here we want to talk about Geomagic DesignX, which was formerly known as Rapidform XOR. It is known as the fastest path from 3D scan to parametric design. We have parametric history-based reverse engineering here, which can create native models for SolidWorks, NX, Inventor, Creo, and Pro Engineer. And those native models are parametric and enable even complex or incomplete scans to be turned into manufactural designs. Because of that parametric approach, we can get the design intent instead of just the shape. So we can also work around some defects or holes, incomplete scans or whatever, so we can create the whole part as a manufacturable part. We have a complete 3D scan processing system which can work with data from any 3D scanner, or not only 3D scanners, it's any digitizing device. So as computer tomograph or MRI or even long-range scanner, so every point cloud or mesh generating device. And therefore we have a very powerful point cloud and mesh processing algorithm inside. The software is fast and highly automated in creating designs from reality, and we do that by using a step-by-step wizard and to extract the CAD features from scan data. And we can also do hybrid solid and surface modeling, so we can cover a variety of part types. And we have the accuracy analyzer, which ensures the accurate models. So this accuracy analyzer is basically mapping the part with a color map of the deviation between the reverse modeled part and scan, or checking various properties of the part. So the competitive advantages are, it's the fastest path from 3D scans to your CAD software, because we work seamlessly with your existing CAD. And you can virtually scan anything and create manufacturing-ready designs, industry-leading scan processing tools. We handle billions of scan points, and we have the ability to create CAD directly from point clouds, and it's easy to learn and use, because we have a software that is very similar to the CAD package which I mentioned before. Here are some applications for redesign. Best applications about aftermarket design, automotive, medical, aero, defense, and mining, or about design modification, or designing into or around the volume. So for example, on this right side, this car, could be scanned. The underbody of the car and the exhaust pipe, for example, can be modeled collision-free into the underbody of the car. Modernization of manufacturing, which includes generate CAD for old parts. For example, if there is no CAD present, or remanufacture broken parts or retrofit parts, or moving to CNC and digital databases in case there's only a paper drawing maybe. Okay, on the output side we have the 3D systems production systems. Here as an example the Pro X series and the iPro series. This is just a selection of 3D systems printing machines. Those are for direct production, so you can directly print a metal part. Now I will show you a live demonstration about how to get from a 3D scan to a manufacturable or printable design. And this is the part which we want to see, and we will just get to this. So I just opened the scan into Geomagic Design X, and as you can see this scan is quite coarse because maybe the part has some bumps and so on from the casting, or maybe it's a prototype from clay or whatever. So the scan is coarse and the scan is incomplete because we cannot scan the inner part. And with that coarse and rough and incomplete scan we can make a very clean and watertight productive model. And the scan is not aligned in the coordinate system, but I can align it to the coordinate system quite easily by just extracting some of the features and generating axes from the part. So what we can see here that this is a cylinder, but the software at the momentary time doesn't know that this is a cylinder or a revolution. So we have to tell the software, please check this part for features. So now the features are detected based on the different curvature. So whenever the curvature changes, we get a new segment. Here we can see a cone, a cylinder, a blade, another cylinder, a sphere, and so on. So we have all this information already inside a part, and we can grab it and generate features for CAD. So the coordinate alignment is quite easy. You can just extract the cylinder axis or revolving axis. In this case I will extract the revolving axis just by picking some of the features and just accepting this one. So we have the revolving axis here. This is our primary axis. Then we want to have the outmost position into this direction from the part. So I will create a plane using the extreme position method, and we want to use this axis as direction, and we want to have the extreme position in this direction, and we want to have the extreme position from this part. And now here is our plane. So with that plane and then in that vector we can create a point which is later our origin. And now we need another axis because this part is still freely rotating around that axis. So we need another axis, this up axis. And we can generate that by getting a symmetry from the section from this part. So I will create a section through this. And at this position I am not sure where I'm cutting. Am I cutting at the most widest position or not? So we have another arrow here. We can generate the silhouette from that feature and project the silhouette here. So in the silhouette I can just get a center line by just creating the center line somewhere and then clicking the line feature and double clicking on this outer line. And fixing this one, and then I'm using the mirror function and just mirroring over this side, this line to the other side, and then fixing those points here as well. So now I have the center line here, and now I'm ready to align the part. So to align the part, we have this interactive alignment, and it creates a split view. On the left side you see the current situation, and on the right side you see the situation after the alignment. So what I'm doing is now check the position. So I'm putting that part into that position in the origin. And check the x-axis. So we want to have this one as x-axis. And as you can see here, this part is aligned to the x-axis. Now I need the y-axis as well. So we have the y-axis as well, and we can flip the axis or flip this axis, so until the part is in the coordinate system as we want to have it. And now I can use the perpendicular views to look from the front or from the top or from the left side on the part. And those features are not necessary anymore because we already aligned the part, so that is just helper geometry. And now we can start reconstructing the part from those base planes which are already in the project. And we have a lot of wizards. I talked about it before, those wizards to extract the geometry, because we have here already a cylinder, a revolution, and so on. So I can create a revolution basically from this part. I'm just selecting those features. And with the right click, insert merge, I'm starting the revolution wizard. And this revolution wizard gets all the features which are around that axis, and it will automatically search for appropriate axis in the coordinate system. So if we have the part aligned to the coordinate system, it will also use the axis, and it will also use the sketching plane, and it will insert the solid. Okay, I need to uncheck one thing. This one more, this one, and this one. Okay, that's the demo effect. Okay, fine. Now I have this revolution body, and this revolution body is automatically extracted from the automatic section through this scan data. So we can just accept it, and we can just evaluate how the quality of this part is. So if we are here inside the 0.1 millimeter tolerance, which I said before, and we can check with a higher resolution as well to see the deviation. The blue areas and the red areas are areas which I did not model yet. So we will go on with modeling with the second feature. The second feature is, let's say, this flange here. And this flange, before I did this one relatively automatic. So I will do this a little bit more manual to show what we can do in the 2D sketch. So basically we grab this plane, this top plane, and I go to Mesh Sketch. Mesh Sketch is basically like a CAD sketch, but we have a reference to the mesh here. We have a section or a silhouette from the mesh, and we can directly snap on this section or silhouette in the 2D sketch and draw our 2D CAD sketch on it. So in this case, I'm just cutting the part here and projecting it down to the sketching plane, and we have a draft angle around here, so I can check this draft angle here, and I can automatically estimate the draft angle from the mesh. So it's estimating, in this case, 1 point something 25 maybe. and I can visually check it as well. Let's say 1.5 degree draft angle. So now we have 1.5 degree draft angle. And with OK, I'm starting the 2D sketcher. So in the 2D sketcher, I have methods like in CAD. So I can, for example, draw a center line from this origin to here horizontally, and I can get a circle, and now I can just double-click the outline, or just click the outline and double-click and get this circle directly from the projected, drafted scan section. And I can put some dimension in on here, so 12.93, or let's say I want to change it to 13. And I can get this one here as well, another circle 4.939, let's say 5. So I can put my design intent in here, and I can go on with dimensioning like this. So you can see when the dimensions are placed, then the lines are getting black when they are fully defined. So I can also use the mirror function, and I can check whether the part is actually symmetric or not symmetric. And now it is the design intent. Is it the design intent, or is it manufacturing tolerance, or whatever it is? I can choose to be symmetric or to deviate from the symmetry and build the part as it is. So this is my choice. And now I can say I want this diameter same as this, or this radius the same as this, and I want to have it maybe perpendicular down from here, vertically down from here, and at another distance. Okay, and now I will trim those pieces away. So we have one contour, and I can use a fillet function. Let's just ignore the value, and let's just pick here and drag the fillet to the appropriate value. And with the accuracy analyzer, we can check the deviation also in 2D, so we can see here how our deviation behaves when I change this radius. I can put a dimension here, it's 15.5, let's say. And on the other side, I can put another fillet. As well, check the dimension and put the dimension 8, or let's say 9, or maybe 10. And again, use the symmetry or use another fillet. Let's say specify the value and use the same fillet here again. So this is basically the 2D sketch. Now we can extrude this 2D sketch to cover this shape. And before we checked 1.5 degree draft, so now we can enter this draft here as well, and we can check our assumption was correct if everything is inside the green tolerance area. And we can also extrude to the other side. We have the same draft here, but this direction. Okay, and it will be merged with the other part. So now let's see the whole deviation of the part. So we have still a little bit too much material on here and too much material here. Let's focus on the upper part. So here we can cut away this, just making a section or a silhouette from the scan data. So if we cut here, we cut just only there and there, two positions. But if we cut, if we don't cut, if we use a silhouette, then we project the whole outline of this part to the center line, which helps us to be more precise here. So I can just click here and directly get this angle, and everything is much more precise than just picking 2 points. So in this case, we can cut by this line. We can use this as tool and this as target, and the cut is done. Now we need to select the remaining part and check the deviation, and in this case the deviation is within tolerance, quite good within tolerance, micron or 10 micron, something like that. And on the other side we have as well a little bit too much. So now here we cannot cut because there is another feature in there, but we can do an offset. So let's say I will offset this in the other direction, 2.75 to the inner side. Ah, come on. This is the demo effect. Okay, we have another method how to do that. So we have not only the offset, we can go back in the parameter and we can go to that extrude which we did before. So in the parameters we can just change this parameter and check the deviation while we are changing this parameter. So we can see here we have 0.1 millimeter or something like that. So I will go to 2.8 millimeter maybe. And now we still have some draft angle around here. So we can already draft this face. So we use the neutral plane draft. So this is our neutral plane, and we have draft faces. We have draft face here. And we can automatically detect the draft in this area. And we can check in the direction, in this direction, 1.5, let's say 1.5. So it looks quite good. Let's say 1.75. 1.75. Yeah, it looks even better. So we can recognize there is only one region of color. So we just need to get this 1/10 of a millimeter inside, and we are in the green area, or 6.5, something like that. So basically this way we can go arbitrarily accurate, just controllable. So our neutral plane here, and the draft face is here, and the direction is this direction, and check it. So now we have done this one. Okay, yeah, basically this is the revolution wizard based, and this is the extrusion manually. So we have always two methods, wizard based and manually, to create such a parametric feature model. And yeah, basically the other features are done in the same way. And yeah, that's the quick demo. Now we have time for some questions.
Thank you, Tobias. You have now the possibility to ask questions. We already have a couple of questions, so I start. How can the software help me to extract the design intent from the scan?
Okay, the design intent can be extracted from scan using those region groups, which I generated at the beginning. So those region groups contain the curvature information, the feature information of each region, and we have several wizards which recognize those feature regions and create cat features from them. So for example, what we saw in the first time was the revolution wizard. So I can just pick this one pick this region and right-click and can say Insert Merge, and it's automatically detecting there is an axis for this cylinder, and it's searching for other features which are similar, which belong to that axis, and it's automatically creating a revolution design. The same way we can also check, for example, this area. We can check this area as well. And it's opening the extrusion wizard because it's an extrusion. And in this case, it's also recognizing that we have 1.59 degree draft angle. So such feature wizards are helping us. And on the other side, we have also modeling helpers. Like, for example, if you want to make a fillet, then you can just pick a line, and you can just say, I want to get a fillet on this line, and I can push this estimate radius from mesh button, and it will automatically estimate or automatically measure the radius in the mesh and will enter the value here. So you have the fillet with that value. So we can get the fillet around here, and we can get the next fillet around here, for example, and measure fillet radius from scan data. So measure this fillet is not very useful. Let's measure this fillet. Okay. And then continue the fillet around here. So in this case, we can see it's not completely modeled yet. We skipped one part, but in this case, we can get the feature information from scan data very easily. And it's also possible to get a variable fillet. So in this case, I will show you the variable fillet. Just push the same button here as well. And so the fillet profile is drawn here in this chart. And you can see the fillet goes from a certain point to a certain another point, and it's moving a little bit up and down. In this case, that might be scanning inaccuracy or wear and tear on the part or something, what happens with that side. But it could be design intent, and so we can match the fillet also flowing to that area.
Okay. How can I check whether a design is printable or generally manufacturable?
Okay, the design as it is not yet printable, but we can generate a mesh from it, and we just convert this body back to a mesh, and the mesh itself is of course printable. So we can compare that with the original mesh. Let's see the original scan, and we have the properties here. In the properties, as you could see in the beginning, the scan is incomplete. It has holes, it has some small defects and everything, and you can calculate the volume here. So it's showing you, oh, I'm picking the wrong one. This one I want to see. So this one is incomplete, and it shows an approximate volume because it is 6% open, this mesh. So it's not completely watertight. This is as it comes from the scanner. And you can estimate how much printing material you need. This is already possible, but it's an estimated value. And if you take this other mesh, this is generated from the CAD data which we created just before. This one is exactly, I picked the wrong one again. So this one I need. This one is exactly closed. This is watertight, and it shows the exact value of volume of the mesh. So the mesh is watertight and it is printable. No material is flowing out. And of course, if you don't want to print the material, if you want to mill the part, then you need to check that it will be processed with a post processor for the CNC machine or something. So you need to check the part consistency as well, and this can be done using the accuracy analyzer. The accuracy analyzer has a continuity check, and this continuity check will check for the surface-to-surface continuity here.
Okay, thank you. Does the software help in analyzing the stress points that can arise from manufacturing or repetitive use?
Stress. No, it's actually not a finite element software. It's actually a software which detects features from the scan. So if we have a scan which is worn, which is a little bit deformed or something, then it would detect a feature deviation. So it would detect, for example, let's do something like that. It's an interesting question. So we have kind of smart brush, a sandpaper here. So we could manually smooth out a little bit, or some of it smooth out a little bit here, or maybe even deform, something like that. So we can make a bump here. Okay, and then we can go to the region grouping, and in the region grouping we can recalculate this region. So I go to the region group, and then I'm taking this cylinder, delete it, and I preserve existing regions and recalculate it. So this will be not a cylinder anymore. So this is a cylinder. This is now a cylinder still because we have some tolerance in it. So if the bump is bigger, then it would not be a cylinder. But we recognize this as a cylinder because we have some outliers here. So let's see if we clean something out from that region. So we could also say we want to remove that. We could use the split function, limit to this region. And we could use the split function to split out an area like this. And this is not taken into account when we talk about that cylinder, something like this. So the regions can be modified, can be detected like here. So for example, if this bump is too bigger than the this threshold for the cylinder, then it will be taken out. I don't know whether this answers your question enough, but maybe you can formulate that by email. We can discuss a little bit longer about that by email also.
Okay, next questions. Are the drawing files compatible with CATIA, and what is the extension of the drawing file?
Okay, we have no drawing in this program. We have a part file, and this part file is called XRL, but we can export everything. We can export the scan as, of course, let's say, as the proprietary file formats, and also as STL neutral file formats or BRML, something like that. And if you're talking about the solid bodies, then we can export about those file formats. So I just step Parasolid, ACES, CATIA as well. CATIA, if you have the exchange license, then you can export to CATIA v4 and v5 as model or CAD part. Or for live transfer to other applications, we can transfer the complete parametric feature history into those applications. It's SolidWorks, Siemens NX, Creo Pro Engineer, and AutoCAD Inventor, Solid Edge newly. And CATIA v4 and v5, as I said before, is saved as CATIA v4 and v5 part.
Okay. You can make planes and axes to use for alignments. Is it possible to make best fit cylinders and use them for the alignments?
Yes, that's also possible. So, for example, if I want to match this part to another part, let's say it would be a kind of part A should be reversed and part B is the one I have. So, for example, I'm creating just a CAD cylinder here. Does not necessarily be that same diameter, but it needs to be that same feature. So if I have that CAD cylinder here, and I want to move one of those cylinders to that one, then I have the datum alignment, and I can say I want to move this scan, and I can change, I can check the datum pair. So for example, I can check this cylinder should move to that cylinder. So you can see it will be moved here. Or I can say this plane around here, this plane should be moved here. So I can virtually assemble this situation.
Okay. With the software, can we make dimension control for scanned parts?
We can get the dimension of the part out of the scan. That is the situation. And once we have the part, once we have this CAD, we can alter the dimensions, of course, because we have everything parametrically here. And we can, for example, for my first revolution, I want to change that diameter, for example. So I just double-click this sketch for the diameter, and I can just get the dimension here. So it is 11.705, and I want to have it 11. Then I just change it. So of course I need to fix the other situation here, say 11. So then it changes just this part, or I say 12, something like that. So in this case, I'm detaching from the scan, of course, and only this part has changed.
What is the difference between this package and Geomagic Design Studio?
This package is more targeting industrial, or let's say this package is more targeting prismatic design. So if we want to have very industrial shaped features, then we are using this package. And the other benefit is if we have a CAD package which is already using a parametric history tree, then we have this parametric history tree here which we can transfer one-to-one to the CAD package. So this is the best software if you are already working with a CAD package and you just want to transfer the part reversed here into the CAD package. Studio, on the other hand, is more freeform oriented. So if you have wider freeform shapes and if you need to be more flexible without the parametric history, then you can use the Studio package.
And for simple scans, can the software fill holes?
Of course, also we can fill holes. So in case we want to fill holes, just let's make some holes. I'm using the paintbrush to make holes. For example, this one. There's a nice hole, or let's say small holes around an area like this. So basically we can fill holes using right-click and fill hole. This is a single hole filling, and it's just checking the surrounding curvature of the part and filling the hole curvature based and smoothing the boundary of the hole. But it's also possible to use a hole filling tool to fill multiple holes, and this has more sophisticated features like bridging or filling gulfs or removing insulas, something like that. So I could just fill that hole in one go, but yeah, maybe it works, maybe it's failing. If the hole is like this, then it should work, of course. If the hole is bigger, then I can also use the bridge function, so I can just bridge the hole and make 2 or 3 different segments and then fill 2 or 3 different segments for the hole. Or I can fill a gulf. That means I can pick a point here and fill part of the hole and continue filling parts of the hole. So it's quite sophisticated hole filling.
I have a last question for you. We have seen geometric features like cylinders, but could you show us some curved surface based on spline or Bezier?
Okay, I have another model prepared. So this model, for example, it's an incomplete scan. This freeform is the one we want to have a look at. So in this freeform we have big holes. So normally if you use second generation reverse modeling, tools, you need to draw splines based on this freeform surface and fill the patches between those splines and so on. But in this case, we have the possibility with the region group to extract the design intent that this is a feature, this is a freeform feature basically, and we can merge this together, merge this to one region, and then we can just right-click on it and we can say insert merge, or we can right-click and say mesh fit. In this case, insert merge would be the extrusion, and insert merge would be a mesh fit. So in this case, we have two methods. We have a method by allowable deviation, so it will just drag this software onto the freeform region based on this allowable deviation. Or we have the possibility to specify a number of control points. So in this case, we can modify it a little bit, and we can say we want to see by allowable deviation. Let's have the preview. And here you can see we are within the 0.1 millimeter allowable deviation. And our environment mapping, basically this ZBrush shading, is a little bit bumpy because the part is as well not very even. So if we want to have a design surface, then of course we can go back and change this, and we can create a design surface with an arbitrary number of points. So let's say 10 by 10 would be the same, but I could also create a real design surface with 4 by 4 control points. And this of course is much nicer to look at, but we deviate a little bit more from the scan data. So it is our decision whether we want to get a surface as built or if we want to get a design surface. This is the parametric way to get this surface, but we have also another way to get this surface, which is the automatic way. So in this case, for example, if we have only freeform, if there is no prismatic or parametric shape, then we can also use auto surfacing. So auto surfacing basically has two different methods as well. We have an evenly distributed network, which is creating basically square patches or something like that. And we have the feature following network, which is following the feature of the shape. So we could just go into the preview, and because this is an automatic process, it has less user interaction, but it has a little bit more calculation time. This is, yeah, this is logical, I think.
Thank you, Tobias. We will now end the webinar. Unanswered questions will be answered individually after the webinar. A record will be available soon in the webinar archive of the Creaform website. Thank you for your participation, and don't hesitate to contact us for further questions or requests.